Hello, dear mentors and fellow Marianopolis students. My name is Izzy, and with my partner Richard, we're going to present the model of our affordable, easy to make and manipulate 3D printed robotic arm. The mindset behind this was to show that 3D printing is also a viable option. So first, we have an Arduino motherboard, which is powered by our computer. A battery could also be used here, but we did not want to buy one. To the Arduino board are attached a muscle sensor that can either be placed on our forearm or biceps, and a servo motor that is placed within the robotic arm. So what happens is that the muscle sensor reads our muscle contraction and sends the value it reads to the Arduino board. Within the Arduino board, we use the Arduino's own programming language to write this program where we first set a threshold value. This threshold value is found by testing several times the contractions value when our muscle is relaxed and when it is contracted. The threshold value is a value when the muscle is relaxed. At the threshold value, Arduino will tell the motor to turn its gears, which we will see in a demonstration appearing at the end of the video, at a 0-degree angle. However, if we contract our muscle, the signal will then surpass the threshold value, and if it does, Arduino will tell the motor to turn its gears at maximum, which is in half circular rotation, so 180 degrees. As the gears are undergoing this rotation, it creates torsion on the strings, which we have surrounding the gears. Hence, the strings get pulled back, thus creating the motion of fingers that close up. And of course, when the gears return to the initial position, the strings are released, and the fingers will then naturally fall back. The system of the whole circuit is connected using jumper wires, and we had to solder the wires onto the muscle sensor so it could be connected to the Arduino board. The motor did not need to be soldered since it came with an adapter. The sensor is plugged into an analog input because it is required to read certain values and then sending them to the board. The motor is plugged into a PWM output because it either reads a 0 or 1. The gears either rotate or not rotate based on the instructions of the board. The negative of both motor and sensor are attached to ground because we want the positive to have a rated voltage. Then the positive of motor is 5 volts, and the positive of the sensor is 3.3 volts, because those are the two power source choices on the Arduino Uno board. You can see up here that the motor is attached to PWM9, a pulse-wide modulation. It basically means that the analog signal we got from the sensor is modulated so that it could be read by another platform, such as an analog servo like the one we have. We plugged it into the 9th slot, but it really does not matter as long as you have it on a PWM, which is the tilt symbol in front of a number. The sensor is attached to A3, but again, it does not really matter since from A0 to A5, they're all analog input. The choice of hardware was pretty simple. We thought that Arduino was the easiest to manipulate with, and MyAware muscle sensor was the cheapest we found. The arm and fingers were ABS plastic 3D printed, which also was the cheapest. And to be honest, they also look pretty good.
As for the structure itself, we used SketchUp to design all the pieces. Each finger, except for the thumb, is composed of 3 pieces, all of them connected through the holes with a separate cylindrical piece. These fingers are then connected together to the palm using the same method. As you can see, there are spaces between each finger, intentionally done, since our fingers normally aren't stuck together like sardines. Within the fingers, there are 2 holes that pass through them. These passages allow the string to pass through the fingers. Finally, some parts are rounded, shown by the orange arrow, while others have this blocky 90-degree section, shown by the blue arrow. The rounded ones are there to allow the finger part to move in that direction, while the blocky part is present in order to block the finger from moving in the other direction. There is then this other piece that represents a makeshift forearm. It is made so that the back of the hand would fit inside within the space between the protruding parts pointed by the arrows. Its use is mostly for the space in the back, where the motor would fit. With this, it will allow the motor to properly work without being pulled forward by the strings. Meanwhile, the space in the front is there to allow some room for the strings coming from the hand to exit and be able to reach the motor, since without it, the cavity where the strings are in the hand would have no exit. Finally, the little saucer was designed to fit onto the motor to try to augment its circumference. Since our motor has a limited range of movement, it can only pull on the strings by so much. By adding this piece that has a larger radius, it will allow the motor to pull much more while keeping the same range of movement. For the strings, we decided to go for fishing string since it is pretty strong while still having some malleability. A lot of hot glue and super glue was then used to make sure that the structure remains as firm as possible. For the 3D printing, if you use your own printer, the materials can be as cheap as $20 for all the pieces. However, ordering it from a company will be much costlier, the lowest being around $230 for all the 3D parts. As such, including everything from the 3D printing to the Arduino board and muzzle sensor, the cost of such a project could range from $170 to $380. While this might sound a bit costly, it's still much cheaper than your usual prosthetic, with a cosmetic one going for $5,000, a functional one going for around $10,000 if it ends with a split hook, and the high-tech Maiware ones that are controlled with muscle sensors can go from around $20,000 to $100,000. This is why 3D printing can be a much more affordable alternative to the current market. Here is a little video showing our product at work.